So you spent a couple of lectures on line integrals, and what I want to do in this lecture is I want to introduce a different type of line integral. So this one is an integration with respect to arc length. So in this case, what we're looking at is we're looking at integrals of this form here, where C is some sort of curve, but the difference, earlier we looked at integrals of the form f dot dr along a curve, but now we're looking at something slightly different. We're looking at a scalar function in this case. And what we're looking at here, we're integrating with respect to arc length. So this is what's called the arc length element. This is the length measured along the curve, basically. It's called the arc length element, and we want to calculate integrals of this form. Okay, so here's a little picture of what's going on. So you have a curve C, and the way that we normally thought about it, that we would have a location R, and you're thinking about parameterizing the curve as well, right? So as you go to different values of the parameter, the R will go to some different point. Okay, and what we did was in the earlier situations, we wanted to make sense of dr, the vector dr. So we looked at the point R plus dr, and then the vector dr was the vector which lay in between them. Now I want to look at something a little bit different because I want to make sense of this arc length element. So the arc length is the length which is measured along the curve. Right, so you take, you take a string, I guess, and you lay it along the curve, and then you straighten out the string, and you just measure how long it is. So S is a measurement. You start at the beginning of the curve, and this point has S equals 0, and then you're just measuring along the curve. So this is sometimes called the arc length parameterization. So it's possible for you to use exactly S in order to parameterize this curve. But in general, you would use just something else t. But the arc length parameterization is sort of special, that ensures that when that this gives you the length along the curve. Okay, so here, so the point R, your general point R, is associated with the arc length S, and then when you increment it a little bit, when you go to some a point slightly nearby, that increments the arc length. There's this extra distance that's added, right? So that's essentially going to be the length of that. So one way in which you can make sense of this is to go back to our understanding of R and R plus dr. In this case, we thought of this dr as being this vector, this yellow vector, which is drawn between these 2 points. And we're thinking of this as an infinitesimal object because it's a differential element. So essentially, we're thinking of this as delta R and making delta R getting incredibly small. So the dr vector that you draw here actually is essentially tangential to the curve. And the more you shrink in and you shrink in and you shrink in, this part of the curve is beginning to look more and more like a straight line. Having said that, then we can say something about the arc length ds along that curve, because this is going to be looking more like a straight line in the infinitesimal limit. So it's just the length. It's just the length of the vector dr, the norm of the vector dr. So that's what we need to do in order to put it back in there. Okay, let's figure out how we can do this now. Okay. Now, dr, you might remember, so was given by, well, it's the increment. Yeah, it's the increment of your position vector. So you've got an increment in x, an increment in y, and an increment in z. We can write this in terms of the differential elements. And now what we need to do is we need to then figure this thing out, because this is what we want. We want that arc length element. We want to be able to figure it out. So this is telling me that all I need to do is I need to find the length of the vector that's given over here. Right, so the length of the vector is the norm of the vector, and that's quite easy to write down. So I take dx quantity and I square it, then I take dy and I square it, and I take dz and I square it, and then I take the square root of all of this. Right, so that's going to be the length of this vector. Okay, so that's pretty nice. So I'm going to write this slightly differently now. See, I haven't bothered to put down the parentheses around them, but this is the more normal way in which you can write it. So it's dx squared plus dy squared plus dz squared. That's the length of this. Okay, this still doesn't make sense in the sense that it's still difficult for me to do an integral with respect to this, right? So if I've got an integral sign in front, how on earth do I do this integral? Right? There's x, dx's, dy's, and dz's. It's really hard to do. Okay, so again, we have to appeal to the fact that our curve has to be given parametrically. So assume our curve is given parametrically. So t varies along the curve. It can be any parametric representation. So you got your x coordinate, y coordinate, and z coordinate, each of which is changing with respect to t. So we've got this. We got this sort of variation. Now, how can that help us? Now, what I've done here is I've rewritten this slightly. Now remember that when I've written dx squared, I actually have that these parentheses around it, right? So what I've done here is that this is effectively as if I'm dividing by dt squared inside the square root sign. And if I'm doing that outside the square root sign, I have to have a dt. Okay, so I'm doing this in a very formal sense, but you can actually make this quite rigorous in the sense that you're thinking of this as a delta t, and you can think of this in some sort of limiting sense. But anyway, so you're just dividing by dt squared inside the square root. So then you have to have a dt outside the square root. Once you write it like this, things look a little bit nicer. In the first place, if I'm trying to do an integral with respect to ds, now you can see that I've replaced it with the differential element dt. That's much nicer. So you just express limits in terms of t. So here's the idea. We want to replace everything in terms of t, just like in the previous situation. But we've got this stuff over here. Now, what does that mean? Well, dx by dt is, well, it's the derivative of this. It's the derivative of this. Dy by dt is the derivative of that. That's the derivative of that as well. So you can see that these three elements, before you square them, those two elements are the components of dr by dt, or of r prime of t. Yeah. And then what you've done is you've squared them and added them together and then taken the square root, which means that you've taken the norm, or you've taken the length of dr by dt, which I'm going to write as r prime of t here. So this is pretty neat, because what we discovered here is that this ds, this arc length element, I can write it purely in terms of t, and this is in a very nice format because I've just got one differential element here, so I can actually that helps me do the integration. So let's summarize what we have here, right? So we figured out in the analysis right now we figured out that the arc length element can be written in this way, and that helps us interpret integrals of this form. So f is a scalar field which changes depending on where we are. C is some sort of curve out here, and we parameterize the curve, right? So general location is r of t. Let's suppose it goes from t equals a all the way up to t equals b. There's an orientation, right? So we're going in a certain direction along the curve. So this is the integral that we want to do, but we want to do the integral with respect to arc length, right? So arc length is once again, it's kind of measured along the curve, right? So s is measured along the curve in this instance. Okay, so we want to do this, and what I've done here is I've reinterpreted the terms, but I'm maintaining color coding to make sure that we're on board. So the ds has to equal that, and that's what we've just argued. So the f in general is a function of r, where r is your location, but the point is that your location as a function of t. So now we can write f as a function of r, which is itself a function of t. And now, because I've represented the dt over here, I know that any limits that I put down here must be the t limits. So that goes from t equals a to t equals b. And what I can see here is that this is purely a t integral. It's a single variable t integral. Yeah, something that you're quite comfortable with using from Maths 1 and so on, right? So this is the process of how you do it. Let's do an example. The semicircular wire below has a linear density, right? So a linear density. So this is a wire. It's a semicircular wire. It has a linear density, and what I mean by that, it's the mass per unit length. Yeah. So this is a wire. If I take one length of this wire, it has this sort of this density, and it's given by this expression over here: rho xy equals x plus y plus 2a. Right, and what you're asked to do is you're asked to find its mass, and I should mention that here a is a positive quantity. You're asked to find the mass of this object. So what this is telling you is that depending on where you are, the density is actually quite different. It might be made out of a lot different material. It might be sort of highly dense at some places and less dense at other places. But it's a wire, and this is how the density varies along it. And we want to find the mass of the total wire. Right? So you want to add together all the little masses, right? If you like, right? So add together all the little masses that you have over there. So what do we do? So what I'm going to do first is I'm going to parameterize it. So the obvious parameterization, this is part of a circle, is I do my standard parameterization of a circle. R of theta equals a cosine theta plus a cosine theta in the x direction, and a sine theta in the y direction. So I do that. But in this case, I know that theta equals 0 is over there, and theta equals pi over 2, and theta equals pi. So this is my limits that I need to put in for my parameter. So I'm using the parameter theta as opposed to t because, well, it doesn't really matter, right? So one is English, one is Greek, but it doesn't matter. Okay, so Now, what do I need to do? Now, you might remember that to find the arc length, I needed to find r prime of theta. So if I take r prime of theta, just differentiate this, that's easy enough. So when I differentiate this, what I get is this thing over here. I get minus a sine theta, which comes from this, and then I get a cosine theta, which comes from that. Okay, and the reason for my doing this is because I want to figure out what ds is. So here's what I've just calculated, and what I've written down here is just a statement of all the things that we discussed a little earlier on in this lecture. But the point is that ds can be written as r prime of theta d theta. That's the whole point. And in this case, that tells me that what I have to do is I have to take the norm of this vector, the norm of that vector. So it's going to be this thing squared plus that thing squared, and then the square root of that. So it's going to be that a squared sine squared theta plus a squared cosine squared theta. But because sine squared plus cosine squared is equal to 1, you just get a squared inside the square root. So it's just going to be an a. So your arc length element ds is going to be a times d theta. Which is quite nice. And in this case, you can argue this by just looking at radians as well, right? Because you know that the length, so if you have theta, angle theta, and then you do another angle d theta, this length is going to be a d theta, right? And that's the arc length is actually measuring a length. So it's all good, right? So all pretty consistent. So everything's fine. So we got that going for us. Okay. Now what else do we need, right? We got the density. The density is given as a function of x and y. It's a scalar field that's given over here. It's a function of x and y. But the point is I want to write everything in terms of theta, in terms of my parameter. So my general location on this wire has a location a cosine theta in the x direction and a sine theta in the y direction, which means this is my x of theta and this is my y of theta. Right, so these two things are these things. So what I want to do is I just take these values and I plug it into this expression over here. So I now know that rho as a function of x of theta and y of theta is given by this over here. I need x plus y. So x is a cosine theta, so that's x. Y is a sine theta plus 2a. So I get this expression over here, right? So I get a, well, 2 plus cosine theta plus sine theta. This gives me my density as a function of theta. Now, so what is the total mass? Yeah. So here is an indication, and I'm using this to show you why these sorts of integrals are actually useful. So here's an integral of a scalar field integrated with respect to arc length, but this actually does give me my total mass of the wire. And the reason for that is this is a linear density, that's mass per unit length, and this ds is well a length, right? So this gives you dm, which is a mass of a tiny segment of the wire. So we had our wire over there, and this is the mass of a tiny segment of the wire. Yeah, and that's given by that. If you prefer, you can think of that as dm. Right, this stuff over here, you can think of this as dm, and you got a sigma in front. So you got an integration sign in front, and integration sign is just an elongated s. It's a summation. Right? You're summing together all the small mass elements. So we can argue that this is the case. So this is the sort of integral that we need to do, and now we're well positioned to do the integral because we've written that in terms of theta, and we've written this in terms of theta, as you got up here, right? So we've written ds in terms of theta, we've written rho in terms of theta. So now it's just a question of doing the integration. If I substitute these values in, so this is what I get. And the point that I want to make here is that now this is a purely single variable integral. So you don't need anything multivariable anymore. You convert it to a single variable integral because you're integrating along the curve and you're using theta as a parameter which varies along the curve. So all you have to do is just go ahead and do the integration. So I'm not going to spend any time doing the integration. This is a fairly straightforward integration. You do your calculation and you get this value here. It's 2a squared times pi plus 1. No units are given to us in this case, right? So that was given to us without any units. So we just write down the answer without any units. So that's it. Okay. Now, just to summarize what we have so far, or just some of the elements that we've discovered so far when we're doing line integrals, both the line integrals of the type f dot dr and line integrals of the type f ds. Right? So so in either of those types of line integrals, we need to have a certain understanding. So we got some sort of curve. R is a general location on the curve. So a general location would be given by xi plus yj plus zk. We are working in 3 dimensions. Usually, the line element is given by this quantity over here, and that's what happens when you just move your r to some other point. R plus dr, it gives you that line element, and the arc length element. The arc length element gives you the distance measured along the curve. Yeah, and that's going to be the length of this vector dr, and that's given by this over here, right? So that's something that we know, but the whole point is whenever you're trying to do an integral, it's best if you parameterize it. You think of your r as a parametric form. So you got your t, which is varying along the curve at different points along the curve. So your r is now a function of t. Each of these x, y, and z are functions of t. Your line element, which was given by the stuff which is just yellow in this expression, you convert this into something with respect to t by dividing by dt and multiplying by dt outside here. So when you do that, you got your dr is equal to dx by dt. So you just need to take the derivative of this in order to find that term and that term and that term. So your dr you can express purely in terms of dt, in terms of t and dt. So similarly, your ds, so what did you have earlier? So you had, so what you had earlier was you had dx squared plus dy squared plus dz squared. So you divide by dt squared all the way through inside the square root, and you multiply by a dt outside the square root. And when you do it this way, you can see that your arc length element can be written purely in terms of your dt, and all of this stuff can be calculated if you know these functions x of t, y of t, and z of t. Okay, so that's how you do an integral with respect to arc length of a scalar function. But these elements, all of these elements are relevant in doing line integrals, in doing any sort of path integral.